Hello, 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 hello. Assalamu alaikum. Now is okay. Thank you. Assalamu alaikum. This is our third lecture today. I'm sure you know that I'm very lucky to meet you for the third time, but I'm not such lucky because it is very tired. But I'll try to go through the third lecture, which is titled Replacing Stoichiometric Reactions with Catalytic Cycles. Actually, this is very important part in chemistry as a whole and in industry because it changed. This is a kind of a change of stoichiometric, which is normal reaction, to catalytic reaction. If you remember in the first lecture, we introduced the difference between catalytic reaction and stoichiometric reaction or uncatalytic reaction. The first difference was the catalytic reaction needs less amount of energy. However, the uncatalytic needs a high amount of energy. The catalytic reaction has small or little of side products, but vice versa in uncatalytic reaction. The catalytic reaction has a lot of desired product because of selectivity, but the others in uncatalytic reaction needs has little of the desired product. Actually, we will take an example of organic chemistry. Organic chemistry always make reactions in the in functional groups, which most probably has leaving group. This leaving group, like this kind of example, which leaving group all has a problem, little problem, which is this leaving group. If it is very expensive, it will cost you twice. The first one is for buying these additional reagents and also for disposing of the waste. We will have a problem for environment as well because of this reaction. We can see here, for example, Ullmann reaction. This is aryl iodide and with copper in presence of high energy, it gives biaryl plus copper iodide. We have a problem here in this reaction. The first one is this copper iodide, if you calculate, of course, you will know that copper iodide molecular weight is 317 gram for mole. 317 means 317. Means if you make a reaction, only 1 mole of this reaction to get only 1 mole of biaryl means you will have 317 gram of copper iodide you need to get rid of. It has two problems. The first one is you bought copper to make this reaction at first. You spend money in the giving this reaction high energy, high amount of energy. The third very problematic issue is copper iodide. Copper iodide is very heavy, which is 317 gram for mole. If you make 100, if you make 10 moles, 10 moles only, then you will have more than 3 kilograms of copper iodide. You need to get rid of it. This means you have a lot of problem in disposing the byproduct, which is the waste. And I think according to our previous lecture, if you try to calculate the atom economy of this reaction, you will find it very low or very high. It will be very low. The atom economy is very low because most of the amount or most of the mass which enters this reaction is going to waste products. So you will have a problem. This is first. Second is, of course, organic people know that iodoaryls is the best for this reaction, and also they act as living groups. Something. Let's go to the main point of our talk. So we have to replace copper with another material which can transfer this reaction from stoichiometric reaction to catalytic reaction. Catalytic reaction means it will be much easier in energy, better in the product, and the side product will be very small. So let's go to try to do this. Can we do it or not? Of course, if we ask this question, basically, if we ask this question, means it can be done. But we will explain how can we do. We will use palladium instead of copper. Of course, somebody may say, oh, you will use palladium instead of copper. Please, professor, palladium is very expensive and the copper is much smaller or cheaper than palladium. Yes, it's basically you are right. But with on the long run, it is incorrect. Means if we use palladium, of course, its copper is palladium is much more expensive than copper with 200 times. But palladium has a very important character or very important property that palladium can be reduced from palladium 2 to 0 with hydrogen. This is very important. That means it is like you can. It is not disposable. It is not used for one time like copper. It is used for one time, 100 times, 11 times. No. 100 times, 1,000 times, and so on. This means it is frequently used. So it will be on the long run. It will be much cheaper than copper. This is the first issue. The second character is it will not have such problems that copper causes for the environment because you will not have this. You will not have the side product which you need to get rid of because palladium X2 will be reduced with hydrogen to palladium 0. And the side product here, we came to the side product of HX, means it is much smaller than HX if we will use, for example, if we will use Cl instead of X, this means you will have only 38 grams per 1 mole. In the previous state or the previous case, in case of copper, there was 317 gram per mole. This was a very big problem. The second is this has another advantage, which is this is a gas. The other was solid. This is a gas. It's easy to remove, but the other was solid. Was very difficult to get rid of. And this is a total reaction will be like this. This aryl halide with in presence of hydrogen and the presence of palladium, biaryl will be formed and HX will be the byproduct. And another, we will have to think about decreasing this byproduct more and more. How can we decrease it? Of course, if we replace if we replace X with H, it will be much easier and better from the atom economy point of view. Of course, if we use benzene with benzene like this, of course, this is theoretical. It can be, I don't know, I think it's difficult to be done, but this is theoretical. We can think about it, and we can do it one day. Benzene with benzene will get biphenyl. This has 100% atom economy, and of course, there is no waste in this reaction. This is another reaction. It is the same reaction, but using palladium chloride as a catalyst, as a reactant in presence of acetic acid. It will give, of course, only chloride as a byproduct, and the biphenyl will be there. Now, this is another example of this reaction. Now, we will go to a very important part in kinetics, in catalysis as well. How can we compare two catalysts, one catalyst with another? How can we compare? Of course, we can compare it with the kinetics of this catalyst and the other one. How can we? There are, if you remember, I discussed with you about the active sites. People try to compare catalysts to each other with the life of this active site. How can we calculate the life of the active site? Simply, we calculate how many of the reactants will be converted to products on this active site. It means how many times this active site will transfer reactants to products. This is the way we compare reactants or catalysts to each other, like this. This is kinetic expressions. We will talk about kinetic expressions. We will we will have to know how much is the active sites we have and how many molecules of the reactants transferred to two products. This is very important to calculate the kinetics or these calculations. First of all, we will talk about turnover number. What's turnover number? Turnover number is the number of product molecules formed per surface site. This means you have to calculate how many surface sites you have, or how many molecules of the active site you have, and how many molecules of the product you have. This is by this division, converted molecules to products over number of active sites, it will give you turnover number. And this is very important, turnover number. Of course, you can calculate, yes, of course, you can calculate the number of active sites. It is virtual. Again, it is virtual, means it is not real. Why, doctor, you are telling us it's very important? It is crucial in our calculations, and it is the way that we compare every catalyst to another one. And now you are telling it can't be calculated exactly, because simply in heterogeneous catalysis, I told you that the reaction occurs on the surface. Adsorption occurs and the reaction occurs on the surface. Bulk doesn't work at all. In chemistry, in heterogeneous catalysis, bulk doesn't work at all. Okay? How many sites you have on the surface, and how many sites or how many molecules of these active sites are embedded or inside the bulk of the catalyst, do you know or you can't know? Completely, I'm telling you, or frankly, I'm telling you, we can't know. It is not known. Only what we have, what we also previously I told you, to know, to do some calculations, we have to make some assumptions to be able to do these calculations. Like I'll tell you briefly, if I tell you that, please give me the calculation 1 over 1 plus 1000. If you have this, of course you will 1 over 1 plus 1000 means 1 over 1000. So you neglect this one to be able to calculate it easily. Okay? In this case as well, we can't calculate how many active sites are there on the surface because there are a lot of other molecules and active sites inside the bulk. We can't calculate it. So theoretically, we know that how many molecules at, as overall in this bulk and on the surface overall. So we just consider all of them are working. Just assumption. So, and we know how many molecules have been converted from reactants to products. This is what we can know. So just convert or divide converted molecules to products to the number of active sites. And we don't know exactly the number of active sites. So TON is approximately calculated. It is not exactly calculated. The second term is turnover frequency. What's turnover frequency? The expression frequency means repetition. How much it is repeated per unit time. This is frequency. If you, in English words, they are saying frequently. I'm going to university frequently means every day I go or every month frequently 10 times per month or something like this. So frequently means how many times it is it can be done for here we calculate per second turnover number. Over time it gives turnover frequency. This is the number of molecules that are converted to desired to products on one active site per unit time, which is second. Again, number of molecules converted to products per one active site per second of time over per unit time. And here, of course, this is multiplication. It's very easy. So turnover number, we have already discussed about it. Turnover frequency. And now we will talk about turnover. There is TON. What's TON? TON simply is, we just calculate about the frequency, which is the number of molecules converted to products in per one site per 1 second. So if we just invert this ratio, it will give us how much time it will take to convert one molecule to product. This is a turnover number, the inverse of turnover frequency, which is defined as the necessary time to form one product molecule. Now we know about turnover number, turnover frequency, and turnover TON, which is turnover time. What is the specific turnover rate? Specific turnover rate is these calculations what we did before, turnover frequency, the number of molecules which is converted to products in 1 second over 1 meter square, which is the unit of surface area. Okay, turnover rate R is calculated by dividing the turnover frequency over the surface area. If we divide over surface area, we will get to know that the turnover rate. And here I can say that theoretically, if you can make a reaction twice on the same active site, this means this is catalytic reaction or not catalytic reaction. If you make it one time only and it can't be repeated again, this is catalytic or not catalytic? Not catalytic. But if you repeat it again one time, moreover, it is catalytic. Definitely it's catalytic. But the problem is it from the cost time of from the cost point of view, the money, the finance or financial support, will it be costly or not costly? Will it be beneficially or not beneficially? Again, is it useful to do it only 2 times or not? That's why people always say that it shouldn't be not less than 100. But theoretically, to be catalytically in as a theoretical word, catalytic, so 2 times are very okay. But how much did you pay to make this catalyst? We just discussed about we replaced the copper, which is very cheap, with uh, with palladium, which is very expensive. So if it goes to make it only 2 times, that means you waste money to make catalytic reaction. You waste time, you waste money, you waste many things to make catalytic. So it's useless. But if it go to 1,000 times, this is beneficial. Okay, and always catalysis is a magic science. That means it is it saves your money, saves your effort, saves your environment, and do many things that you can't do without it. Okay, if you remember, I discussed about if you want to move to from one city to another, and you can go to your city from here walking, you may take months to go, or days, several days to go. Whenever if you use a car, which is very fast, or an aeroplane, that means this is a magic that you transfer very quickly to the other place. Uh, okay, this discuss what I have just mentioned. Uh, Now we go to what is the reaction probability. Reaction probability is how frequently or what is the probability of completing this reaction. Of course, it can be calculated by it is the rate of formation of product molecules divided by the expected collisions that can be done in this reaction. Of course, we discussed also about collisions, that collisions should have two main characters or two main things should be provided, which is number one, direction, which is the orientation, direction as your sister just said. Second is energy. It should have enough energy and orientation. And I think if anybody have any question about what I am just told you, please let me know. If not, we can go to other part of the lecture. Okay, we can go to other part of the lecture. This is the second part of our lecture, which is the affinity. Affinity. Affinity is very important. What's affinity? Affinity is the uh, is the attraction or the loving sense between uh, reactants and the surface or products and the surface. If of course this is discussed by several people, and especially somebody is called Sabatier. He added a very important principle. We can just ask this question: what is the effect of binding forces between the surface and the reactant molecules? If the binding forces between surface and the active molecules is very high or very low or intermediate, what is the best thing? I think they only we can only have this scheme. It's very simple. Oh, just return back. It's very simple. If you can see that A plus B will be absorbed in the surface, A plus B will react on the surface to form TS, which is the transition state, and this transition state will be converted to product, and this product will leave the surface, which gives the empty surface or clean surface, which again will have absorption of A and B and so on. This is catalytic cycle. And if we cut this catalytic cycle at any point, what is the point? At any point, if you cut this catalytic cycle, like if you didn't absorb, if you didn't make absorption of A and B on the surface, or you didn't make desorption of B on the surface, if you didn't make absorption means that there is no attraction between A and B and the surface. That will not, it will not make any absorption. This is the interaction is too low, no adsorption will occur. This means no reaction will occur. And on the other hand, if P still stick on the surface, it didn't go out, it didn't leave the surface, no desorption. This means it loves the P loves the surface very much. There is great affinity between the surface and the product. This means no reaction will occur. Why? You just did reaction and the P is formed. Yes, P is formed, but it didn't leave the active site for another A and B to be absorbed, and the cycle will go on and one time, second time, and third time, and so on. This is called poisoning of the surface of the active of the catalyst or the active sites. Poisoning. Poisoning means it kills the active sites. It kills the catalyst. This so the affinity from this scheme, Sabatier just mentioned that the absorption of A and B to the surface will be difficult. If the absorption is will be difficult, it means the interaction is too weak. This means no reaction. And if the reaction is so strong or too strong, this means also no reaction. So he concluded that the catalyst is said to be poisoned by the reactant if it's too strong. The successful combination between the catalyst and reactants is when the interaction is not too weak, but also not too strong. It should be intermediate. And even in all of our life, we just check or go in intermediate. We shouldn't be in extreme, either to the right or to the left. This is an example. Shows the binding between catalyst and reactants. Of course, you can see here that if this is a clean surface and metal will take formic acid. Formic acid will form on the surface metal formate. And then metal formate will be decomposed to CO2 and H2O, which will leave the surface and give clean surface again. This is, of course, we repeat this cycle again and again with different reactants and different examples, but it is basic in catalytic reactions. In this surface, in this reaction, we have some things. In this scheme, we have some things to tell you. The first one is each formic acid should have attraction with the metal to be absorbed on the surface like this. And when it is absorbed on the surface, it forms metal formate. Metal formate. What's M? Where did you bring this M? I told you in previous discussion or previous lectures that this catalyst takes part in the reaction, devote, sacrifice by himself at the beginning, of course, for this reaction, gives the atoms or even molecules or loose atoms or molecules for the reactants, and then return it back again later. Here we can see that metal will form metal formate. Metal will form metal formate with formic acid. Then after decomposition of metal formate to CO2 and H2O, which are the products, we have two steps here. The second one is the desorption of CO2 and H2O from the surface to give clean surface. The first is the formation of metal formate, and the second is desorption of these products. Sabatier studied the effect of metal to know how it goes, how this reaction will go. He studied this reaction over several metals, as we can see. This is the reaction rate, and this is delta HF, which is the heat of formation of metal formate. And he noticed that increasing the heat of formation at the beginning leads to increase of the rate of reaction for these metals. gold, silver, rhodium, platinum, and iridium until this at the peak. Okay. After that, eh, although the metal, the heat of formation increased, but the reaction rate decreased. He discovered that at the beginning, the heat of formation and the formation of formic acid is rate determining step. When it is rate determining step, this means increasing of heat of formation will lead to increase of the rate of reaction. I am sure you know what is rate determining step. Rate determining step is the step that determines how fast the reaction will go. It's like when you go with your little brother or sister on the street which is 2 years old. Who controls the walk of course, the little man will control your walk. Okay, this is the little man. RDS, rate determining step. In Arabs, we say that الضعيف سيد الركب, which means the weak man who is the king, is the king of our walk, because we should walk in his speed. But after by the end, the rate determining step is being the desorption of CO2 and H2O from the surface. This is the rate determining step. Then the best conditions for getting more decomposition of formic acid is the intermediate values of the rate of adsorption and the rate of desorption. When the rate of adsorption and the desorption are intermediate, then we get the maximum catalytic activity. And this is again Sabatier principle. It discusses what we just said, and this figure is important figure because this is the delta HF and the rate of reaction that we just discussed in earlier slide, and this is another figure which shows that this is the temperature to complete the reaction, and this is delta HF. At this point, which is this point, this is the temperature. Of course, high catalytic activity means you can go in this reaction at less temperature. This is the high catalytic activity. Okay, at this point. Uh, this one. At this point, we can say that again he is telling what I have just mentioned several times. And thank you very much. Thank you. If anybody has any question, I am okay to discuss with you. Yes. Would you please out of record? Okay. Yes, brother.